please.
Okay. Good morning, everyone. I'm Cong Yi from the Central China Normal University. I apologize that I'm unable to present in person due to the visa issues. First of all, I'd like to thank the organizer for giving me this opportunity to present my recent work here. The title of my presentation is the hydrodynamic effects on spin polarization in AA and PA collisions. This talk will include our newest numerical results about the spin polarization across the Rickettsian and scan region and the star fixed target program. This is the outline of my presentation. First is the introduction, and then we will use the hydrodynamic model and the transport model to study the global spin polarization and the local polarization at AA and PA collision systems. At last, we will conclude with a summary. Let's begin with the introduction. As we know, the huge angular momentum generated in the heavy collision will lead to the global spin polarization of lambda hyperons. In addition to the global vorticity along the total angular momentum, the coagulum plasma has more complicated local vertical structure. For example, the local vorticity induced by the V2 and the V3 will lead to the local spin polarization of lambda hyperons. According to the different choices of the spin quantization direction, we can categorize the spin polarization into the polarization along the beam direction, the polarization along the total angular momentum, and the helicity polarization relative to the particle's momentum. Recently, many works have extended the global equilibrium to the local equilibrium and found besides the thermal vorticity, there are some other effects can also contribute to the spin polarization. They are related to the shear viscous tensor, fluid acceleration, spin Hall effects, and the electromagnetic field. Since the electromagnetic field decays rapidly in the heavy collision, we will neglect its contribution in the following discussion and call the other four contributions as the hydrodynamic effects. Note that the second line is also known as the shear-induced polarization, and the fourth line is also known as the spin Hall effect. After considering the shear-induced polarization under some assumptions, the theoretical calculations can qualitatively and quantitatively agree with the experimental data at 200 GeV gold-gold and 5 TeV lead-lead collisions. These new hydrodynamic effects on the spin polarization have been studied by many works at high energy large collision system. How about their contributions to the spin polarization at lower collision energy and smaller collision systems? Our following works will try to concentrate on this question. We first use the hydrodynamic model and the transport model to study the global and the local polarization in gold-gold collision at Rickettsian and scan region and the star fixed target program energies. We use the 3 plus 1 dimensional viscous hydrodynamic framework CR-VISC to describe the evolution of the coagulum plasma. For the Rickettsian and scan region, both the energy momentum conservation and the net Bayesian current are considered. The equation of motion for the dissipative current are described by the second order S-like equation. For the initial condition, we choose two different type partonic and hadronic initial condition, AMPT and SMASH. The whole AMPT model can well describe the evolution of coagulum plasma individually. But here, as the initial condition of a hydrodynamic simulation, we just use its hygiene and ZPC part. The initial partons are generated in the hygiene model, and then their 2 to 2 scattering are described by the ZPC model. When the system reaches the hydrodynamic initial time tau zero, we can get the location and the momentum information of our hadrons. Well, the particles in the SMASH model are hadrons. Similarly, we can also get the get the information of our hadrons at tau zero. Then we can use the Gaussian smearing method to get the initial energy momentum tensor and the baryon current. Here the G denotes the Gaussian smearing function. Sigma r, sigma eta represent the transverse and the longitudinal smearing waves. After the evolution, we can get the hydrodynamic gradient information at the freeze-out hypersurface, and then we can use the spin-Kuiper-Frey formula to calculate the spin position induced by the different source term. In order to compare with the experimental data, we further transfer the spin position to its own rest frame. Finally, the local spin position is given by the average over the transverse momentum and the rapidity. If we further integrate over the azimuthal angle, we can get the global spin position. There are our numerical results about the global position as a function of collision energy. The left figure is the results just induced by the thermal vorticity only, while the right figure is the results considered our hydrodynamic effects at the local equilibrium. We can find under these two different cases, the theoretical calculations can both agree with the experimental data quantitatively. This means the influence of these new effects on the global spin polarization is about 10 to minus 4 or 10 to minus 3 power, which are much smaller than that induced by the thermal vorticity. Therefore, the global spin polarization is mainly contributed by the thermal vorticity, and it will increase with the decreasing collision energy. Whether the global polarization will continue to increase as the collision energy decreases further until to the threshold energy for the lambda production. Some works predict that the global spin polarization or the kinetic vorticity will reach a peak at a few GeV, but the current experimental data shows that the center value of the global polarization will keep increasing from 5 TeV to 0.4 GeV, while the polarization of lambda hyperons keep rising with the decreasing collision energy. If not, how large will the tuning energy will be? At such low collision energy, hydrodynamic model and the AMPT may no longer be applicable. So we use the hadronic transport model SMASH to describe the evolution of the system. The baryon stopping effects have been considered in this model. We first extract the energy momentum tensor from the particle's momentum. The flow velocity and the energy density are the eigenvector and the eigenvalue of the energy momentum tensor. Since the global spin polarization is mainly contributed by the thermal vorticity as a preliminary result, here we just concentrate on the thermal vorticity effects. Based on the thermal vorticity of the collision system and the last interaction location of the lambda hyperons, we can calculate the average global spin polarization of lambda hyperons by the spin polarization vector. The left figures summarize the current numerical simulations given by the 3FD model and the AMPT model compared with the experimental data. The right figure is our numerical results given by the SMASH model. The blue and the red markers are the experimental data. The black lines are our the black line is our numerical results given by the SMASH model when the impact parameter equals 6 Fermi. We can find it will increase with the decreasing collision energy when the collision energy is larger than 2.4 GeV, and the green lines green line is our numerical results when the impact parameter b equals 9 Fermi. We can find it will reach a peak at 3G at around 3 GeV. The tuning energy depends on the impact parameter and the they and these two lines represent the boundary of 20% centrality and 50% centrality. Therefore, our numerical result for the 20% centrality to the 50% centrality should be between them. After the average, the peak of the global spin polarization is smaller than 3 GeV. We have also studied these hydrodynamic effects on the local spin polarization at the Rick, bin, and scan region. They are our numerical result about the spin polarization along the bin direction as a function of azimuth angle. The three upper figures as a result with the AMPT initial condition, and the figures at the lower panel are the results with the smash initial condition. We can find that the blue lines are the local spin polarization induced by the thermal vorticity. It will always give a minus sign to fine-tuned, and but the orange line represents the shear-induced polarization. It always gives the positive contribution at different collision energy and the initial condition. The red lines are the spin Hall effects. We can find that it will increase with the decreasing collision energy and show strong dependence on the initial condition. Another experimental observation of the local spin polarization is the second Fourier coefficients of the spin polarization along the y and the z direction, which are also known as the P2y and the P2z. They are the amplitude of the local spin polarization. We further use the hydrodynamic model to study the spin of the P2y and the P2z across the Rick, bin, and scan region. The left figure is the P2z as a function of collision energy. The red and blue markers are the experimental results. We can find it will change its sign at lower collision energy. The different lines represent our numerical results with different parameters. We can find our current model cannot describe the experimental data for P2Z at the Rick, bin, and scan region. The red figure is a P2Y as a function of collision energy. The red markers are the P2Y of lambda hyperons. We can find it will increase with the decreasing collision energy. But the P2Y of lambda bar hyperons, the blue markers will decrease with the decreasing collision energy. Our current model cannot both describe both of them with a single initial condition. Does this imply there are some new effects we haven't considered? In the condensed matter, when a charge current goes through the materials under an external electric field, a transverse spin current will be generated. It's called the spin Hall effect. In the heavy collision, by replacing the electric field with the shear force and the gradient of the bionic chemical potential, we can get the shear-induced polarization and the bionic spin Hall effects. Recently, our group found that after we consider the interaction effects, an actual spin current appears. This current flow in the opposite direction to the spin Hall effect. So it's called anomalous Hall effect. This phenomenon is also found in the condensed matter in this paper. The anomalous Hall effect can also contribute to the spin polarization. Um, the corrections has the following expressions. Here the G1 and G2 comes from the scattering, but do not depend on the coupling constant explicitly. The correspond correspond to the anomalous Hall effects in the condensed matter. More details about this deviation can be found in this paper. Can we observe the anomalous Hall effects in heavy collisions? Therefore, we use the hydrodynamic model to simulate this novel effect. There are our numerical results compared with the experimental data. The left figure is the P2Z as a function of collision energy. The blue and the red markers are the experimental data. The blue lines is our previous simulation without the anomalous Hall effects. But after we consider these new effects, the results turn to the orange line. It can well describe the experimental data. The red figure is the P2Y as a function of collision energy. We can we can find after we consider the anomalous Hall effects, the theoretical calculations can describe the experimental data better. At last, we have also studied the spin polarization at p-led collision systems. Since the total angular momentum cannot be well defined in the p-led collisions, here we just concentrate on the spin polarization along the beam directions. Recently, the CMS collaboration has measured the local spin polarization of lambda hyperons along the beam direction P2Z as a function of multiplicity at 8 TeV p-led collisions. We can find the magnitude of the polarization at a small system is at the same order as that in the A collisions, and it will increase with the decreasing collision energy. But the V2 in the p-led collision will decrease with the decreasing energy. These results seem to contrast the picture that the P2Z is induced by the V2. Therefore, we also use the hydrodynamic model to study the spin polarization in the p-led collisions. We first use the parameterized Trento 3D model as the initial condition and consider the constituent distributions in each nucleus. In the transverse plane, we choose the ITP plasma-like entropy decomposition with A equals 0. For the longitudinal direction, we construct the function form by parameterizing its cumulant generating function. The subsequent evolution of the system is simulated by the CR-basic hydrodynamic model. For the 8 TeV collisions, we will just focus on the energy momentum conservation equations. Here, the temperature-dependent shear viscosity and the bulk viscosity are given by the Bayesian analysis in this paper. The equation of that are provided by the Hot-Q-City collaboration's results, and the result temperature is said to be 154 MeV. We first use the charged particles multiplicity and the V2 of lambda hyperons and the charged particles to calibrate our numerical parameters. Our current model can well describe these observables, and then we use these parameters to calculate the spin polarization in the p-led collisions. For the 8 TeV p-led collisions, here we will neglect the spin core effect and concentrate on the spin polarization contributed by the thermal vorticity and the thermal shear tensor. In addition, we have also considered 3 different scenarios. In the lambda equilibrium, we assume the lambda hyperons reach the local equilibrium at the freeze-out hypersurface. So we can use the spin core formula to calculate the spin polarization of lambda hyperons directly. At the S-quark equilibrium, it assumed the spin of lambda hyperons is mainly carried by the constituent S-quarks. At the isothermal equilibrium, the temperature gradient will be neglected. Note that the numerical simulations at the S-quark equilibrium and the isothermal equilibrium can partially describe the experimental data at high energy nuclear collisions. There are our numerical results at 3 different scenarios. The left figure is the P2Z as a function of multiplicity. The red markers are the experimental data, and the blue lines and the orange lines represent the spin polarization induced by the thermal vorticity and the shear viscous tensor respectively. We can find the shear-induced polarization always give a positive contribution, and the polarization induced by the thermal vorticity is always negative under these 3 different scenarios. The total P2Z is given by the black lines. We can find our numerical result cannot explain the experimental data under these 3 different scenarios. The red figure is the P2Z as a function of transverse momentum. Again, we can find our numerical results is inconsistent with the experimental data. To test the influence of the bulk viscosity, we further turn off it to calculate the spin polarization. There are our numerical results without the bulk viscosity. We can find it also cannot explain the experimental data. In contrast, we use the spin polarization of lambda hyperons to calibrate our parameters and then calculate the V2 of lambda hyperons and the charged particles multiplicity. We can find the parameter can describe the spin polarization at the S-quark equilibrium and the isothermal equilibrium cannot fit the multiplicity of charged particles and the V2 of lambda hyperons. Therefore, the P2Z of lambda hyperons is not only induced by the V2 in the p-led collisions. New non-hydral effects need to be considered in the polarization at a smaller collision system. At last is my summary. In the spin polarization at Gold calculation for the global spin polarization, we find the influence of these new effects on the global spin polarization is much smaller than that induced by the thermal vorticity. And the tuning energy for the global spin polarization depends on the impact parameter. For the local spin polarization, we found the anomalous Hall effects will play an important role in the lower collision energies. For the spin polarization at the p-led collisions, we found the shear-induced polarization always give a positive contribution, but the polarization induced by the thermal vorticity is always negative. The result, our numerical results are inconsistent with the experimental data. Therefore, new non-hydrodynamic effects should need to be considered in the polarization at a smaller collision system. That's all of my presentation. Thanks for your time.
So, any questions?
Um, the spin Hall effect, it's preliminary, but this looks really interesting. I mean, I have a couple of comments. I mean, how qualitatively, how does the spin Hall effect sort of change the phase from by pi over 2? I mean, this is the puzzle. And the other thing is, if I remember correctly, the longitudinal polarization persists at the LHC, where there is no chemical potential and there is also no spin Hall effect, I guess. Yeah.
Yeah, at the high energy collision system, I think the spin Hall effect will be small because the bionic let me because at the high energy collisions, the bionic the chemical gradient will be small. So this effect will be important at the lower collision energies. And for the reason why the anomalous Hall effect can change can explain the experimental data. I think we don't currently we don't have a clearly physics picture about this.
So, any other questions?
Hi, so thank you for the talk. I have a question regarding your slide 15, please. So, yeah, for the lambda
15.
polarization, 15, yes. For the lambda polarization, you're showing three lines there, and it seems to have three different equations of state. Do you understand
Mm,
why does it change so much depending on the equation of state? Do you have a physics pictures for that?
okay. Uh, this uh this the figure the the left figure comes from the Heday's paper, and the numerical simulations uh, comes from the other group. I think uh, at the lower collision energy is better for use the hadronic equation of state. And why? Actually, I don't know why why mm, why the crossover equations of state can better explain the experimental data. Uh, okay.
So, let's thank the speaker again.
Okay.
Our next speaker is Georgii, okay. Oh, yes, please.
for possibility to give a talk in this beautiful place and for the hospitality. You can see the title of my talk on the slide, and I will tell about results obtained by me with my group, Dmitry Lapygin, Oleg Teryaev, and Valentin Zakharov. Here is the contents of my talk. So I will start with introduction and motivation. Then we'll move to main part, in which I discuss the calculation of shear viscosity in the accelerated frame for different spins. And then I, in the third part, will analyze the obtained results, in particular discuss the relation with entanglement properties and correspondence between local and global quantities. We know that there are a lot of interesting effects at the intersection of quantum field theory and hydrodynamics, such as chiral magnetic effect and chiral vertical or axial vertical effect, which, as we know, are closely related to the axial anomaly in the gauge field. Also, there is an interesting result about thermal part of axial vertical effect, which is controlled by gravitational chiral anomaly. And let me mention the result obtained a few years ago by us, that there is one more effect of gravitational chiral anomaly, which we call kinematical vertical effect. It arises in the third order in gradients. There are two terms. One is vertical term, and the second term includes acceleration. And the correspondence with anomaly is described by this formula. Here is the factor from the anomaly. So it splits between these two conductivities. And it is interesting that this result can be obtained from basic conservative equations. So this derivation can be compared to classical derivation of Son and Surovka. So we can conclude that acceleration is important for transport effects, and this motivates us to consider it in more details, because unlike vorticity, acceleration is discussed much less in this context. Let me give reference to the talk of Aritra, in which he discussed some interesting effects of acceleration for the leptons. And there is an interesting effect. It is well known for many years, related to acceleration. So by equivalence principle, it can be shown, for example, that there is a partner effect of Hawking effect in the accelerated frame. It is so-called Unruh effect. So the essence of this effect is that the Minkowski vacuum is perceived by an accelerated observer as a medium with Unruh temperature, which depends on acceleration. So if we consider two observers, so static observer see Minkowski vacuum at 0 temperature, and accelerated observer will feel finite temperature. And several years ago, there was interesting development, which started with this paper of Francesco Beccattini. The statement is that we can have obtained a new point of view to the Unruh effect from the point of view of quantum statistical methods. And the statement is that the direct consequence of the Unruh effect is that if we find mean value of operators, such as stress energy tensor operator, it includes corrections with acceleration, and Unruh effect means that these quantities should be 0 when temperature equals Unruh temperature. And just as an illustration and example, For spin 1/2, we have such formula which depends on temperature and acceleration. Let me emphasize that this formula can be obtained without any use of curved coordinates, so we work in usual flat space. However, we see that really, if we put this temperature here, then it will be 0. Most of the effects which I mentioned are believed to be non-dissipative. However, as we see, for example, from the previous talk, and also I want to mention the talk of Daniel, shear is also very interesting. It can contribute, as it was shown in this talk, to Wigner function and contribute to polarization. And there is a famous result related to shear viscosity, that there are no completely ideal fluids. And there is a bound to the shear viscosity, so the ratio of shear viscosity to entropy density should be higher than 1/4π. This is Kovton-Son-Sterinets bound. Just to give you some feeling how it was originally obtained, we use holographic principle and connect conformal field theory in the limit of strong coupling with classical gravitational theory in higher dimensional space, 5-dimensional. And in this case, shear viscosity is related to cross-section of scattering of gravitational waves of gravitons on black brane, which is proportional to the area of this brane. And entropy is related to the entropy of this brane, which is also proportional to the area. So their ratio will be finite. And there are plenty of works about this bound. So summarizing, we could point out such a problem. So is it possible to connect these two effects, Unruh effect and this bound, to the viscosity, and calculate viscosity for Unruh radiation without any use of string theory and holography, directly using Kuba formulas? And this I will show you. So to do this, we go to the Rindler space, which is described by this matrix. It is related to Minkowski coordinates by these formulas. There is horizon, since 0, 0 component of the metric will be 0 when rho is 0. And rho is related to the inverse acceleration, so this matrix describes accelerated frame. And usually different quantities are singular at the true horizon. So we follow usual approach and introduce a space-like surface which is located slightly above true horizon. It is called stretch horizon. And the area between these two horizons, true and stretch, can be called membrane. Actually, it can be shown that it has hydrodynamic properties. But for us, it is just important that we will consider quantum fields which live above the stretched horizon, which is located here. So LC can be called the membrane thickness. And then we just consider quantum fields in this space-time in Minkowski vacuum state and use Kuba formula. We know Kuba formula for shear viscosity very well, but now we use it for Rindler space-time. In this case, it looks like this. So we can use the fact that we work in Minkowski vacuum, which allows us to calculate this correlator just using usual Minkowski coordinates. And we just go to Rindler coordinates when we find the Fourier transform. And it can be shown that we can go from the retarded green function to the so-called Weitmann function. And we will consider free fields, which means that we find such diagrams. Also, we can consider local and global quantities. Local quantities are related to some point above the horizon, and if we integrate from the stretch horizon to the infinity, it will give us global viscosity, which is related to unit area of the horizon. Also, we need to know entropy, and to find entropy, we use this approach developed by Francesco Bicatini with collaborators. So, from relativistic spin hydrodynamics, it can be shown that in our case, entropy can be constructed just as a derivative of pressure over the temperature at constant acceleration. It is interesting to notice that we see some difference between denominator and numerator, because in numerator we have viscosity, which we calculate sitting in the Minkowski vacuum, and since here is the derivative, to find the entropy in the denominator, we need to go above the Minkowski vacuum. We also use the fact that we work with Minkowski vacuum, so temperature equals en-route temperature, so viscosity will depend only on the distance from the horizon, and we also can integrate it to obtain viscosity, to obtain entropy per unit horizon area. And now I will shortly discuss the result of this paper, where spin zero case was considered, and will give more details of calculation for spin 1/2. For spin zero, we consider well-known stress energy tensor, improved stress energy tensor. Then we need find the correlator of true stress energy tensors. Each includes such universal term, which is universal for conformal field series, and also deviation from conformal field theory. This universal term looks like this. It is important that in the denominator the poles are shifted, because this is Weitmann, in such way, according to the choice of Weitmann green function. We also know stress energy tensor. We find pressure, then we find the derivative of pressure to find entropy. We go to the en-route temperature and find local viscosity and integrated quantity. So finally, we see that we have such formulas for shear viscosity and entropy per unit horizon area, which diverge as the distance between stretched and true horizon, which is typical for Rindler space. However, if we look to the ratio, it will be independent on this parameter and saturates Kofton-Stone-Sterinets bound. If we consider local quantities before last integration, then the ratio will be described by this maybe not so trivial function. Now I go to our result about spin 1/2. For spin 1/2, we also consider Benefanti stress energy tensor. We use propagator in coordinate representation in the form of Weitmann function, which looks like this, and it is important that the poles are shifted upward in relation to the real-time axis. Then we use rather straightforward calculations. So we split the points in this correlator. Then we use Wick's theorem for Weitmann functions, and take into account only connected contributions. Then we just put green function into this formula, find derivative, the trace, and finally we obtain such result for this correlator, which also corresponds to conformal field theory, but with different coefficient, overall coefficient in comparison to scalar field. And then we need to find the Fourier transform in Rindler space. For this, first we integrate in the horizon plane, moving to the polar coordinates. So this integration, so these coordinates are not touched by translation to Rindler coordinates. And this integration can be done directly, analytically. Then we need to find the integral over the Rindler time with finite frequency from Kuba formula. And this is the key moment, because here we have the poles of the third order. Actually, there is infinite sequence of poles which look like this. These poles are located along two vertical lines parallel to imaginary time axis. And we need to find this integral along the real time axis. However, we can use the property of periodicity of the integrand and close this contour. So the integral over the closed contour can be related to the integral which we are interested in by this formula. And we see that only two poles fall inside this circuit, and we find the residues in these poles. Then we find the limit of zero frequency from Kuba formula. And finally, we obtain such formula for local viscosity at some distance from the horizon, which then can be integrated to obtain such formula for viscosity per unit horizon area. We also need to find entropy density, and we do this in the same way as for scalar field. However, it is important that here we also have a square term, which, unlike scalar field, contributes to entropy density. And finally, we find such local entropy and integrated entropy per unit horizon area. And we see that both shear viscosity and entropy will be different in comparison to scalar field. However, again, their ratio satisfies the Coughton-Son-Sterinets bound. And moreover, if we consider local quantities, their ratio will be described by the same universal function as for scalar field. Then we move to spin 1 case, and for spin 1 we consider RC gauge, and the stress energy tensor in this case rather well known. Includes Maxwell part, gauge fixing part, and Fadeev-Popov-Ghosts part. And we also know Whiteman function for electromagnetic field and for ghosts. And depending on which part of stress energy tensor we include, there will be 5 contributions. However, it can be shown that mixed contribution with Maxwell part and gauge fixing part are 0, and gauge fixing part and ghost part cancel each other. So we need to find only the contribution of Maxwell part finally. And this is the result. So again, both of these quantities are different in comparison to spin 0 and spin 1/2. However, the ratio again gives us the Coughton-Son-Sterinets bound, and the ratio of local quantities give the same universal function as for lower spins. So what we see? We see that Unruh radiation is characterized not only by finite temperature, but also finite viscosity, which saturates this limit inspired by string theory. In comparison to holography, it is interesting to notice that in holography, if we calculate the first correction to the Coughton-Son-Sterinets result and consider big but not finite Hooft coupling, then it can be shown that the bound 1/4 pi is saturated in the limit of strong high Hooft coupling. And it is opposite to our case because we obtain 1/4 pi for free fields. However, very natural question is what is the source of this viscosity? Because one could expect that viscosity for free fields will be either 0 or infinity, because we know that viscosity is proportional to free path, and it is infinite for free fields. So one could expect that viscosity will be infinite. We do not have a final simple answer to this question. Let me just give some simple notions which could explain the obtained result. So first, the fact that there is entropy for Unruh effect and Unruh radiation is a very well-known fact. And from the Compton-Son-Sterinets bound, one could expect in advance that also we will obtain non-zero viscosity. Also, due to the appearance of horizon, we can say that our system will be a kind of open system, which is characterized by dissipation. Also, we see that, in fact, we find the ratio of two quantities, and entropy density in the denominator, in fact, is an entanglement entropy. And it is logical to say that in the numerator, viscosity also will be related to the entanglement. So it can be a kind of entanglement viscosity. Also, it is maybe interesting to notice that we have some observation related to the problem of black hole entropy, because for black hole entropy, there is a problem that we can calculate it in different ways using Wittgenstein-Hawking formula, or like entanglement entropy. Both of them are proportional to the area. However, the problem is that this second entropy depends on the type of these fields which we consider. And something like this we have in our case, because the entropy is different for different fields. And the question is how to relate these two derivations. And we see that though both entropy and shear viscosity are different, their ratio will always give the universal number. So this may be interesting in this context. And finally, I would like to discuss the correspondence between local and global quantities. So if we do not find the last integral, then the quantities will describe shear viscosity and entropy at some distance from the horizon. And it is interesting that this function is universal for all the considered cases. It includes logarithmic term. If we go to the membrane surface, to the stretch horizon, then the ratio of local quantities will be 2 times lower than Compton-Son-Sterinets bound. And in the limit of 0 membrane surface, membrane thickness, we will have this ratio 3 times higher than Compton-Son-Sterinets bound. However, for integrated quantity, we have exactly 1/4 pi. Now I move to the conclusion. So first, I want to notice that there are interesting non-dissipative effects related to vorticity and acceleration, such as kinematical vertical effect related to the gravitational chiral anomaly. Also, we calculated viscosity in Rindler space for Minkowski vacuum for spin 1/2 and spin 1. And it is not related to interaction. However, it is related to entanglement. Also, the average values of shear viscosity and entropy are different for different fields. However, their ratio always saturates the Compton-Son-Sterinets bound, which can be interesting from the point of view of relation of different definitions of black hole entropy. And locally, the bound can be violated. On the stretch horizon, it will be 2 times higher, and in the limit of 0 thickness of membrane, it will be 3 times higher. And finally, we can conclude that the obtained result supports the objective interpretation of the Unruh effect. So the interpretation that it is not only the effect of detector, but we have a kind of real medium which has not only finite temperature, but also finite viscosity. Thank you for your attention.
So, do we have any questions?
Yeah, so very interesting talk. I just wanted to check with you if I understood correctly the idea about entanglement viscosity. So first of all, the entanglement entropy. So you have a pure density matrix, which in the case of a horizon, you have to trace over an observed path behind the horizon. So you get mixed density matrix, trace of rho log rho and so on. Yes. So now, when you compute viscosity, then you apply the Kuba formula with 2 energy momentum tensor, and then the energy momentum tensor deforms the system in such a way that the region over which you have to trace gets distorted, and this modifies the value of entanglement entropy. Is this correct interpretation, or you are thinking about something else?
It is interesting question. Maybe I should think about this. However, in the case of calculation of viscosity, the role of entanglement for me is not so clear. Of course, maybe it appears like you describe it now, but in fact what we see that we just use the propagators, which we know we use Kuba formula, but where the entanglement appears is not quite clear maybe.
Mm-hmm. Okay.
Any more questions? Okay.
Hi, Georgii. Thank you for your talk. So, actually, I mean, it may be a very naive question, but my question is related to the interpretation of the temperature in the Unruh effect, right? So, so in this, I mean, as far as I know, you don't need to talk about temperature to start thinking about the Unruh effect. So, you can just start with classical field and look at an accelerated frame, and you will find this. So my question is, let's say you use a finite temperature field theory, right? You're in a scenario in which you want to discuss something that has temperature. How would this temperature in this statistical system be related to the temperature in the Unruh effect? Is this the same thing?
It is important notion. So it is important not to mix different temperatures, because we have temperature of the system and we have acceleration. And these are 2 actually independent parameters. Then you can go to the point when the temperature equals the Unruh temperature, and this just a choice of special state of the system corresponding to Minkowski vacuum. However, real temperature, which you call the thermal theory, it can be different, and this means that we will have another state of the system.
So let's thank the speaker again. Now, Khwahish. Now our next speaker, Khwahish, will tell us about relativistic magnetohydrodynamics in heavy-ion collisions.
So, hello everyone, I am Khwahish and today I'm going to talk about a project that I'm developing with my supervisor Gabriel de Nicole. And I'm going to talk about equations of motion in the framework of relativistic magnetohydrodynamics in heavy ion collisions. So this is the outline of my talk. I'll begin with the motivation of this project, and then I'll talk briefly about the framework of relativistic magnetohydrodynamics, and then I'll finally discuss the equations of motions in strong magnetic field and then in strong electric field, and then I'll end the talk with my conclusions. So as we all know that magnetic fields are very important in many different scenarios. The strongest steady state magnetic fields are found on the surface of a type of neutron star called magnetars. There the magnetic field could be of the order of 10 to the power 15 Gauss. Now interestingly, one of the strongest transient state magnetic fields are expected to be found during the initial stages of heavy ion collisions. There, these magnetic fields could be 10,000 times stronger than those found on the magnetars. And even though these fields decay rapidly in time, but since they are created right after the collision, they might have some detectable consequences. And we know that the framework of relativistic hydrodynamics has been quite successful in explaining the phase-space evolution of quark-gluon plasma. And since the magnetic field of the highest order are being created during this collision, so we consider the interaction of magnetic field with this quark-gluon plasma, and hence the framework of relativistic magnetohydrodynamics. So to put simply, relativistic magnetohydrodynamics is low frequency, long wavelength approximation that couples Maxwell's equation with the framework of relativistic hydrodynamics to explain the macroscopic behavior of highly conducting fluids, for example, quark-gluon plasma. The relativistic magnetohydrodynamic framework operates on the same conservation laws as usual hydrodynamics, that is, conservation of energy momentum tensor and net particle flow current. For now, we only focus on the energy momentum tensor, which is given like this. So we can clearly see that there are some magnetic field contributions. For example, magnetic field correction in the energy density, in the pressure, and also an anisotropy introduced by the magnetic field. And to get the information about how this magnetic field evolve in time, we study Maxwell's equation for the magnetic field, which is given by Hodge dual. And in absence of electric field, Hodge dual assumes this form here. So all good. So to get the closed equation of motion for the energy momentum tensor, the only thing remaining is shear stress tensor. So now the first approach to get a closed equation for shear stress tensor could be Navier-Stokes theory, but we all understand that Navier-Stokes does not produce viable results in the relativistic regime. So the next reliable approach is Ralph-Stewart theory. So that was our motivation for this project. We wanted to understand how is Ralph-Stewart theory behave in presence of magnetic field. So we use the framework of relativistic magnetohydrodynamics to study this specific system. So this system consists of a fluid having two particle species, that is, we have particles having positive charge and negative charge. These particles are massless and point-like. We consider a locally neutral system with vanishing dipole moment, no spin, and we also ignore, just for simplicity, bulk and diffusion, and so we only focus on the shear stress tensor. And we'll be using method of moments to derive the equations of motion. So for this system, we solve the Boltzmann-Vlasov equation, which in presence of magnetic field looks like this. Here we assume collisions to be binary elastic collision, and we do consider the interactions between the same particle species and also the interaction between the particles of the same species and the interspecies interactions. So with this, after some long calculation, we derive shear stress tensors for individual particle species, that is for the positive species and for the negative species. But these individual shear stress tensors are not hydrodynamically observable quantities. So what we do is we sum these two shear stress tensors and call it the total shear stress tensor of the system. And we also define a new field, and we call it relative shear stress tensor, which is given by the subtraction of these two quantities. Now, to get the equation of motion for these shear stress tensors, we have used 14-moment approximation, and this is the main approximation of this whole study. So 14-moment approximation is when, so we know that we can write single particle distribution function like this, where F0 is the single particle distribution function at equilibrium, and the phi is the off equilibrium contribution, and this phi is function of momentum. Now, in absence of bulk and diffusion current, when we can write phi like this is the 14-moment approximation basically. So we write off equilibrium contribution like this, and we get the equation of motion, the exact equation of motion for the shear stress tensors, both for the total and for the relative. Here in this equation, these sigmas are the function of cross sections. Sigma plus minus is the cross section when the interspecies interact with each other. For example, positive species interact with the negative species. And the sigma t is when the same species particle interact with each other. We have also assumed that these two cross sections are the same, that is, cross section when the positive species interact with each other and the negative species interact with each other, they are the same. Under these assumptions, we see that this is the equation, and we find a coupling between the shear stress tensor and the relative shear stress tensor. And this coupling is solely because of the presence of magnetic field. So you cannot solve the equation for the total shear without solving the equation for the delta shear, the relative shear. Now, just for the simplicity, we went ahead and projected the equation for the shear with respect to the magnetic field. And we observed that we have three different components of the shear, one longitudinal to the magnetic field, one orthogonal to the magnetic field, and one semi-transverse to the magnetic field. And when we solve the equation of motion for these three components, we observed that all the components have different equations. They relax differently. So this was a very interesting observation. As soon as you turn on the magnetic field, the shear stress tensor that we usually expect to have just one dynamical equation, it splits into three, and now it has three different dynamical equations, each relaxing on its own. So this was first observation, first result for this project. Just for the sake of simplicity, I'll focus only on the transverse component throughout the talk. So again, for the simplicity, we use the new basis here. So we have for velocity fixing one direction, then magnetic field fixing another direction. We have two more directions left, using which we construct this new basis, and we project the equation for the components of shear stress tensors using this basis. And so this is the equation for the transverse component, the total shear stress tensor transverse component and the relative transverse component. And as you can see that these equations are indeed coupled because of the magnetic field. Now to understand the physics, we linearize these equations around equilibrium and in constant magnetic field, and we assume the homogeneous case. In this scenario, we find that the equation for the transverse component, it behaves like a simple harmonic oscillator. So we find the modes of this equation, and then we had a very peculiar observation. That was, if magnetic field is below certain value, which is given by these quantities here, then, okay, we have the usual expectation that the shear stress tensor will nicely relax to equilibrium by exponential decay and everything's good. But as soon as this magnetic field value becomes greater than a certain value, then we have oscillatory dynamics, in the sense that the shear stress tensor will no longer exponentially decay to equilibrium, but rather oscillates to equilibrium. And this dynamics is not captured by the usual Israel-Stewart theory, so we need something better, maybe this shear, relative shear type of equations to capture this nuance. So we went ahead and we implemented our equation in the simple Bjorken flow where the magnetic field follows this simple profile. And we plotted the longitudinal component of the shear stress tensor and the transverse component with respect to the normalized time and for different values of magnetic field. Here the largest value is like 10 to the power 19 Gauss. And we see that for the, as we increase the magnetic field, we see the hints of oscillation in longitudinal component, and there are clear oscillation in the perpendicular or in the transverse component of the shear stress tensor. And these oscillations are not captured by the Israel-Stewart theory. So this was our peculiar observation from this project. The natural extension is to see how the system behaves in the presence of electric field now. So that is what we do. We use again the same relativistic magnetohydrodynamics framework, and we study the equations for the resistive case, and we, just for the simplicity, we study the homogeneous system. So we have the same system of two particle species, massless particles, all the assumption approximations are the same. And we study the energy momentum tensor, and it's very similar to what we have in the magnetic field case, just that instead of magnetic field now we have electric field correction to the energy density, to pressure, and anisotropy because of the electric field. And to get an idea about how this electric field evolve, we again study Maxwell's equation for the Faraday tensor, and in absence of magnetic field, it looks like this. We also study net particle flow current. So now to have a closed equation of motion, we study the shear stress tensor, but also the electric charge current. So for the Israel-Stewart theory, it gives the equation for the charge current like this, like extended Ohm's law. And this is the shear equation that Israel-Stewart theory gives. And now we wanted to see for large magnetic field how these theory will evolve for our system. So again, the same mathematics. We study Boltzmann laws of equation, which in presence of electric field looks like this. We have the same assumption on the collision kernel, that we have binary elastic collision. We also consider the interspecies and intraspecies interactions. And we also assume that the cross sections are the same when the similar species of particle interact with each other. And for this case, we assume that the interspecies interaction are much larger than the same species interaction, in the sense that positive and negative species interact with each other more than they interact with among themselves. And so as we had defined the shear, we similarly defined the total electric charge current, that is charge current for the plus and charge current for the minus, and we add those two. Then we find the equation of motion for the total charge current and also for the total shear. And we see that even if we just have the electric field in the system, it will produce a shear stress tensor, and this shear stress tensor in turn will impact the evolution of this electric charge for current. And so these equations are coupled but simple, and we solve these equations to get the modes of the equation. And again, in this approximation that the interspecies particles are colliding much more than the same species particle, we see again the similar result, that if electric field exceeds a certain value, we will have oscillations in the system. And so the usual extended Ohm's law can no longer be valid. So again, this system will not be accurately described by the Israel-Stewart theories. And do I have some time? Okay, so I'll also go to the outlook. So we can extend this two-particle system for the heavy ion collision to an astrophysical set, where we have instead of massless particles, we have massive particles, for example, electrons and ions. We solve the same equations. The usual approach that people are using, right, in astrophysical system to study the shear is to approximate shear as just the parallel component. They consider only the parallel component of the shear stress tensor. And but there in the astrophysical system, this approximation works around equilibrium because they have very large magnetic field but really small temperature. However, in heavy ion collisions, we have large magnetic field and large temperature. So this approximation will not work for heavy ion collisions. And also, even in astrophysical system, if the parallel component of the shear stress tensor itself grows large enough, then this approximation break. Then we have to consider other components of the shear stress tensor. And this is our ongoing project that we are investigating, and we hope to see some interesting results. And then, okay, I'll leave my conclusions to you. Thank you.
Any questions?
In plasma with electric fields, you have Weibel instabilities.
Yeah.
Is this your oscillatory dynamics? Or essentially you have these homogeneous small perturbations which grow exponentially?
No, these are not physical. I mean, these oscillations, I don't think they describe this viable instabilities.
Okay.
Yeah.
Why? Yeah.
I mean, this is just the manifest of the theory. If we are able to capture these with this Ralph-Stewart theory, we see these oscillations that are not being captured. But if we see this, we use this shear delta shear equations, then we don't see these physical instabilities.
Any more questions?
I'm also curious about the case with the electric field. When you have electric field and currents, wouldn't you have to include self-consistently also the magnetic fields that will be necessarily induced?
For the heavy ion case, you mean?
Well, in any system, plasma like this, when you include electric field and currents, because of the dynamics, you will necessarily induce magnetic fields.
Yeah, I get it. So this is the next step. I agree with you. We have to include the full electromagnetic set, the electric field and the magnetic field, to understand the actual physics going on there. So yeah, that would be the next step, to add the magnetic field in the electric case.
Okay, thanks.
Yeah.
Any short question? If no, let's thank the speaker again. So now we have an online talk. Dynamic magneto-chiral instability in a semiconductor by Abboud. If you are here, you can start, please.
Okay. Hi, everybody. My name is Nick Abboud. I'm a PhD student at the University of Illinois, Urbana-Champaign. I wish I could be there in person. Had some funding issues, but I'm very grateful to the organizers for providing the opportunity for me to speak remotely today. So I'm going to talk about a new chiral instability that we identified in a materials context. This was a joint effort between experimentalists and theorists. The experiment was led by Fahad Mahmoud at the University of Illinois and carried out and analyzed in large part by Yijing Huang. Rafael Fernandez is a condensed matter theorist, and then my advisor Georgii Prokhorov and I are from the high energy nuclear theory side, all from Illinois. So let's see, yes. So I probably don't need to say much about the chiral magnetic effect, but as a reminder, it's something that can happen in systems of massless fermions in a magnetic field. So roughly you can think that the magnetic field polarizes the spins, and then the right-handed particles move along their spin, left-handed go in the opposite direction. And if there's an imbalance in the number of right and left-handed particles, one gets an electric current along the magnetic field. Although what's hidden in this picture is that ultimately this is a consequence of the chiral anomaly. And we're probably most used to thinking about this in the context of heavy ion collisions. But as I said, what I'm going to focus on today is the materials context, the shiny rock context of electrically conductive crystalline materials. And people are interested in the chiral magnetic effect, in particular in a class of materials called vial semimetals, because vial semimetals realize massless fermions. So I want to unpack that statement a little bit. This is a plot of the dispersion relations for an electron in a crystal environment. These can be fantastically complicated, but for transport properties, usually it suffices just to consider the states near the Fermi level. A semimetal is a material where the density of states near the Fermi level is small. And generically that happens when bands, dispersions which are approximately quadratic, just barely touch the Fermi level. And in that case, the relevant effective theory is in terms of particles and holes. However, in contrast, in a vial semimetal, the bands can touch at a point near the Fermi level, and the structure of the states near the Fermi level is described, in this case, by a massless Dirac-Lagrangian, or a combination of right and left-handed vial fermions. So one would expect the whole machinery of relativistic quantum field theory to be imported, and in particular, maybe the chiral magnetic effect shows up in these materials. And also the nodes, the crossing points can appear at different energies, so it appears that even in equilibrium, perhaps right and left-handed particles can be in different number, and that there would be then a chiral magnetic current in equilibrium. However, this is not taking into account the ultraviolet cutoff provided by the lattice, and accounting for that properly leads to the maybe more expected conclusion that the current cannot exist in equilibrium. So the system needs to be driven out of equilibrium, and one nice way of doing that is by leveraging the chiral magnetic effect itself, which says that in static electromagnetic fields, charge can be pumped from one node to the other, and then eventually this balances with scattering processes to maintain a steady state non-equilibrium configuration in which there can be a net chiral magnetic effect. And there's good experimental evidence in these steady states going back about 10 years. But it's also interesting to ask whether and how this can manifest in transient states in condensed matter. And certainly from the experimental perspective, this is less explored. So one way that it could show up is as an instability. I want to kind of illustrate that with this animation over here. So let's imagine that there's some magnetic fluctuation somewhere, which there always will be. Then this induces a current by the chiral magnetic effect, which produces a circulating ring of magnetic field, which induces a ring of current that tends to amplify the initial magnetic field. And these self-amplifying magnetic fluctuations, in the context of vial semimetals, there are some concrete proposals. For example, it's been proposed that it could leave a signature in the reflection coefficient of helical light from a chirally pumped steady state vial semimetal. But there's still room to look for genuinely transient effects in condensed matter experiment. But it seems, from this picture that the essential ingredients are just Maxwell's equations and a current that goes with the magnetic field. So provided that one can find the current going with the magnetic field in a different context, suggests that this instability could be more general. And just as a cute example from a different field, in fluids, in charged rotating fluids, as a consequence of a helical turbulence effect, one can get a macroscopic current going with the macroscopic magnetic field. And in fact, this is part of a dynamo mechanism by which stars can create and maintain large magnetic fields. Here's just a very pretty simulation of a neutron-star merger in which the treatment of the magnetic field is based upon this effect. So just to indicate that it's done in other fields, and for our purposes, it's a current that goes with the magnetic field with no massless fermions in the system. Suggesting, as I said, that, let's go to the next slide, that we can ask, what other condensed matter systems can display a current going with the magnetic field that may come with an associated instability. So let's look to symmetry for a second. I'll introduce this tensor sigma b. Under time reversal, both the magnetic field and the current flip. So sigma b is time reversal even, and we don't have to consider magnetic materials, as we could have guessed from this vial semimetal context. Under parity transformation, magnetic field is axial and the current is polar, so sigma B is parity odd. And that means that the crystal structure of the material that we're seeking should not contain any centers of spatial inversion symmetry. And mirror plane symmetry is a little bit more interesting because the current and the magnetic field, the parallel and perpendicular components transform differently under reflection across a plane. This doesn't prohibit sigma B, but in order to get a current component parallel to the magnetic field, which seems to be an ingredient to this effect, one should prohibit mirror symmetries as well. So we're looking for crystals with no orientation flipping symmetries. So these are chirally structured crystals that come in a left and a right-handed variety. And the one that we focus on in the paper is elemental tellurium, whose crystal structure is characterized by these helical chains of tellurium atoms. And then the symmetry analysis shows that sigma B can exist, provided that it's axisymmetric, and I'll assume that it's isotropic in what goes forward. But we still need to drive this system out of equilibrium somehow into a transient state and have a way to measure the evolution of the system as a function of time. And there's a very powerful experimental technique for this that our experimental colleagues specialize in, called time domain terahertz emission spectroscopy. What they do is they put the tellurium in a magnetic field, send in an ultra fast, very short laser pulse, which excites some transient state that then re-radiates terahertz radiation that can be collected over here. And here's an example experimental trace of the electric field over time. This orange signal contains, it turns out, just a handful of decaying resonances, which in tellurium are widely attributed to impurity levels because other sources other modes are absent at the same frequency. I'll say more about impurity levels in a moment, but the striking thing is that indeed, in this decomposition, actually one of the oscillations is exponentially growing, and very robustly over temperature and magnetic field. So this is certainly something unusual for this system, and it smells like an instability. So we wanted to know if magneto-chiral effects could be playing a role in this instability. As a very first zeroth order attempt, we can ignore everything that makes this a condensed matter problem and look at just the consequences of a current going with the magnetic field. This is by no means new. From Maxwell's equations, you get a modified wave equation that's saying that the acceleration of the magnetic field is driven by its rotation. So this is like the cartoon animation from earlier. And searching for plane wave solutions in an infinite space, with this sign convention that I've chosen, an imaginary part of the dispersion relation that's positive indicates an exponentially growing solution. And indeed, as summarized nicely in this review, that's exactly what you find. So there is an unstable mode, at least for long wavelengths. However, exactly when it's unstable, it's also perfectly non-oscillatory. So this is on its own not capable of accounting for the growing oscillatory mode that's observed in experiment. So we need a new ingredient, and we suggest that the important ingredient is the impurity levels themselves. So this is because the impurity level, as I mentioned before, sets the scale for the oscillation frequency. Impurities, roughly speaking, for us are pieces of charged dirt in the crystal structure, and they can be thought of as charged harmonic oscillators, which contribute a bound current to the current density. And then as a generic consequence of this, so here I have the impurity oscillators are represented by this horizontal line. They couple with electromagnetism, and the dispersion relations rearrange into this black line. This is the polariton mechanism, which is an old phenomenon. What's important for us here is that this mechanism produces a partly electromagnetic mode whose frequency is pinned at the frequency of the impurity level, which we put in by hand. So because also the charge carriers are coupled electromagnetically, we can ask whether the impurity polariton can somehow inherit this instability through this mediated interaction. And to address this question, we made a simple modification to the first attempt by adding the bound current due to impurities. And also, we found that we need to add a frequency-dependent component to the sigma B tensor, which is something, so this Drude form is something generic to chiral crystals and is consistent with previous calculations in condensed matter. And we do the same thing, insert into Maxwell's equations and just look at the dispersions. It's a simple calculation. And here again, we see the impurity polariton with its frequency scale set by the impurity level. And one mode, the one that I've highlighted in blue here, acquires an instability. It's propagating, oscillatory, and unstable. And to generate this plot, I used some physically reasonable parameter values, some of which, like the electrical conductivity, could be measured directly on the sample. And the result, in particular, the oscillation frequency and growth rate, agree within order of magnitude with the experiment. So as a proof of concept, I think this is a good indication that magneto-chiral effects are at play. Component of the terahertz radiation. Before I conclude, I just want to draw a few conclusions, draw a few comparisons with the steady state chiral magnetic effect in vial semimetals. One obvious distinction is that this is a firmly transient effect. And in addition, it's a firmly transient effect, and I should point out that, transient effects related to chiral phenomena in condensed matter are kind of I think in the beginning stages, at least on the experimental side. And this appears not to require the chiral anomaly strictly. It appears that only a chiral crystal structure is necessary for this sort of thing. And because of the involvement of impurities, this doesn't have a direct analog outside of the solid state. So I think that this kind of broadens the class of material contexts in which one can expect to see these interesting transient chiral, magneto-chiral effects, to include tellurium, which is a semiconductor. It was chosen because it's very versatile and tunable and ubiquitous. So we proposed a very simple electrodynamic model in which impurities are included in a minimal way, and found an instability which agrees broadly with the experimental parameters of the experimental data. And going forward, we can look for this result and other related effects in other chiral materials. And perhaps somewhere down the road, this could lead to new opportunities for manipulating terahertz range radiation. But I think in the near term, now this problem deserves to be studied in a more systematic microscopic approach, which we're pursuing now. And yeah, we will be excited to see what it turns up. That's all I have. Thank you.
If I'm not mistaken, your group used a linearly polarized pump. Is that correct?
That's correct, yes.
So it's not clear in this case what is the mechanism of creating chiral imbalance in the material. And my question is whether you also tried using circularly polarized pumps, and whether there was any change in the result.
Yes. Okay. I think so. First of all, from the symmetry perspective, this would be symmetry allowed. Even so, I would say the chirality is the crystal structure gives the electron distribution chirality. But I can point to a specific speculative mechanism here for generating a chiral imbalance, which is okay. So tellurium is a time reversal invariant chiral crystal. This means that opposite chirality vial nodes are not related by symmetries, because the time reversal invariance says that the vial nodes come in pairs with equal energy, but it relates pairs of the same chirality. So in principle, vial nodes with different chiralities can have different energies, and therefore can, even by a linearly polarized pump, we expect can be excited with different populations. And moreover, after the photoexcitation, the average rate of decay should depend on the energy gap that the electron has to traverse, returning to equilibrium, which can differ on average between the right and left-handed fermions. And I'm sorry, I know you had a second
no,
question.
I think this is a plausible explanation, but I still think it would be very interesting to try circularly polarized pump.
Yes. So my understanding is that they have some new data with a circularly polarized pump that shows not very much difference from the linearly polarized case, but I'm not sure how to interpret that yet. Yeah, thank you.
Any more questions? Well, if no, let's thank the speaker again.
Thank you.
And now I think we have coffee break.